So can you guys see my screen?
Yes, ma'am.
Okay. Question number 7 was, let f to be a holomorphic function on C minus 0. Means on 0 we does not know about the analyticity, but otherwise the function is analytic with this property that mod of fz is less than root mod z plus 1 upon root mod z. Now we can write it like this also. Now we have to prove that this function f is constant. Any guesses? How can we do that? Have you guys tried this cheat sheet? Sita, do you have any guess how to solve this question?
Ma'am, fz is less than equal to root mod z. We can say from here that m mod fz is less than equal to root mod z.
Not directly, but we can approximate. So first of all, the first thing which we should observe that is this singularity at 0 is removable singularity. For that you can observe that this limit is 0, which will imply that this 0 is the removable singularity. So from this you can observe that you can now remove this singularity and consider this function f to be an entire function. We can remove this singularity at 0 and define a new function which will be an entire function. So we can consider this function as an entire function. Next thing which you should observe that is for any large mod z, say mod z is greater than 100, then you can take a to be 1 by root mod z, which will be less than 1 by 10, which is less than 1. So from there you can observe that mod of fz will be less than some a times mod of z, because mod of z plus 1 for large this one will not play much role. So we can approximate mod z plus 1 as mod z for large values. For example, if mod z is 1 lakh, 1 lakh 1 and 1 lakh, we can approximate them. Is it fine? From there you can see that also you have done this result, right? That if mod z is less than some constant times, then this will be, if it has any power p, then this will be the polynomial of degree p, at most degree p. So it has power equal to 1. So from there you can conclude that f is a linear polynomial. Is it fine? You have done this result? Yes or no?
Yes, ma'am.
Okay. With the same argument, you can also see that f mod of fz can be taken to be less than some constant times root mod z, using the same argument for large mod z. And these two conditions, first and second, will imply that this function f is constant function. Because no linear polynomial can be approximated using the root function. Is it okay? From there, you can conclude that f is a constant function. If you are not able to imply this from first and second, you can take fz to be x plus iota y and then do some calculations to like you can take it as az plus b and do some calculation to conclude that this is a constant function, that this a will be 0. Is it okay? Yes or no?
Yes, ma'am.
Let's move to the tute sheet 5 then. In the last classes, sir, in the classes, sir is trying to teach the integrals, to convert real integral into complex integral and simplify it, some improper integrals. So the question number 7 is of the same types. I'm doing one or two parts. Other parts you can try. Is it fine? Wait for a moment. Can you just give me 1 minute? So first of all, you can observe that you have to calculate x square upon 1 plus x square to the power square dx. The first thing you can observe here is that the degree of the numerator is less than degree of q, and degree, if I write it as polynomial here, the degree of p is less than degree of q. Now you have done the first type integrals. This belongs to the first type. So you can just directly change it into you can in the limit terms. And now you have to change it into the complex integral. How will you change it? What will be the curve? You can observe it. This is type 1 integral. Any suggestions? Aarti? How to change it into the complex integral? You have done this in the last class, I think. Can you hear me?
Ma'am, px by qx into log x.
What are you saying? Can you please repeat?
Ma'am, px by qx into log x.
What is the role of log x? Why are you introducing log here? I'm just asking about the curve. You can change this integral into complex integral. Same z squared plus 1 whole square dz. What will be this curve CR?
Upper half of the circle of radius r.
Yes, upper half of the semicircle, this from minus r to r of radius r. So which singularity will lie in this semicircle? To how to calculate this integral? Now this integral will be equal to this one. So which singularity of this function lies in this semicircle?
Iota.
Iota. So you can apply residue theorem here. To get it residue of this function at iota. Now how to calculate this residue? You can write it as z plus iota whole square on z minus iota whole square. Is it fine? So if you define it as g function, this one, gz, then your answer will be gz right? Please calculate it fast. What will be the answer here? What is the residue of this function? Yes, Harsh, you are going to answer this. Calculate it fast. What is the residue of this function? This is gz. Just you have to calculate g dash at iota. Calculate and give me the final answer. Others also try. What is the value of g dash iota?
And minus 7 by 4 at.
Minus iota by 4. So the final answer will be 5 by 2. Yes, right. Same trick will be applied in the second part. Just the change is here. The integral is from not from minus infinity to infinity. The integral here is from 0 to infinity. So how will you change it into my integral from minus infinity to infinity? Tanvi Meena. Tanvi, how can you change this integral from 0 to infinity to minus infinity? Tanvi, can you hear me?
Yes, ma'am.
You can observe that this is an even function. So integral on right hand side or left hand side will be same. So the I will be half times of my integral from minus infinity to infinity. Now the same trick, you can convert it into the limit of this r tends to infinity from minus r to r, and choose a curve to be semicircle of radius r. Now what will be the singularities here in the semicircle? How many singularities will be there inside the semicircle?
2.
There are two poles inside the semicircle. One is of order 1 and
And
other
the
is
root
of order 2. Yes. Root 2 iota and
2 iota.
2 iota. So your final answer will be half times 2 pi I residue of this function. Let this to be fz. Residue of this function fz at root 2 iota, some residue of this function at 2 iota. You will calculate this. This root 2 iota is a pole of order 2 and 2 iota is a pole of order 1. Right? Now you have to calculate the final answer. You can do it.
Yes,
Yes,
ma'am.
ma'am.
I'm leaving it as an exercise. Fine. So other parts you can try. If you are not able to calculate, you can just message me. Okay. Other parts are left as an exercise. Now let us discuss the sixth question. What is the sixth question? That given a meromorphic function pz upon qz, where pz and qz are the polynomials, complex polynomials, with this property that degree of q is greater than equal to degree of p plus 2. Then you have to prove that sum of residues of pz upon qz at zeros of q is 0. So how will you proceed for this question? Any guesses? Any guesses?
By argument principle.
How will you apply the argument principle? First of all, you have to choose some curve where you can integrate so that this residue thing comes into picture. Make sense? Yes or no? Yes or no?
Yes, ma'am.
Okay. So first of all, we will choose a contour, simple curve, such that all the zeros of this QZ lies inside it. Now we are choosing some circle of radius r with this property that it contains all the zeros of QZ, plus it is satisfying one more condition. Why are we choosing this condition will be clear in the next steps, where this BI QZ we are writing it as we are taking the QZ polynomial as these coefficients of its coefficients are BIs, right? So we are choosing the R radius R in such a way that this circle will contain all the zeros of QZ, and also it will satisfy this condition number 1. Now you can directly observe that now if I take PZ to be summation of xi z raised to power I from 0 to n, and Cn to be the maximum of all these coefficients n times, then you can observe that this mod of Pz will be less than Cn r raised to power n, right? Is it fine? Assuming the two polynomials as have the coefficients Bi's and Ai's, choosing R in such a way that this inequality is satisfied. Now you can see that mod of QZ will be greater than some RM times mod of Bn, right? उधर वाली साइड की सारे coefficients इधर ले आओगे. Bz half था तो ये बचेगा, which will be greater than mod of Bm by 2 Rm, right? Now we can apply ML inequality to the integral. We are integrating over this circle R. Now this will be less than some R raised to power m minus n minus 1. Is it fine? From the residue theorem, you can see that this integral over that contour C will be same as this integral of radius R residues. Hello, can you hear me? There was some internet issue, I think. Hello,
Yes, ma'am.
can you hear me? Now you can observe that this condition is given, that degree of m is greater than degree of q is greater than degree of p plus 2. So from there you can observe that this right hand side of the integral, this thing will tend to 0 because this is a positive quantity when r tends to infinity. So RHS will tend to 0 as n tends to infinity, which implies that this summation of residue is tending to 0. Is it fine? I know this is a tricky proof. But we are using residue theorem to prove this result. Is it okay? Hello. Actually, your voice was not clear. Can you please speak again?
No, I am saying please repeat it once.
Okay. Okay. First of all, the thing is we are choosing some contour C which contains all the zeros of QZ. Then we are choosing this radius R such that this inequality holds. We are assuming that the coefficients of QZs are BIs and PZ is AIs, right? So using these BIs, we are taking this condition. Now, we can observe that this mod of QZ will be greater than this in terms of this BIs and R, and all same for the mod of PZ is less than, because we have to show it greater. QZ is in a denominator. Now using the ML inequality, we can show that this is less than 4 pi Cn, this Cn upon mod Bm R m minus n minus 1. Okay. Now we are applying a residue theorem. From the residue theorem, we will get these two integrals will be equal to the summation of these residues, and which will tend to 0 as n tends to infinity. Fine.
Yes, ma'am.
Okay. Next is you have to show that the fundamental theorem of algebra using the Roche's theorem. What is the fundamental theorem of algebra?
Polynomial of degree n has at least one root.
Hello.
Yes, ma'am.
Fundamental theorem is that roots of polynomial will lie in all the roots of polynomials will be given in the complex. Complex roots will be there, right? So we are assuming any polynomial of a degree n. We have to show that this p has n roots in C, right? Yes or no?
Yes, ma'am.
So what is the Roche's theorem? First of all, please tell me what is the Roche's theorem. Let me ask. Sanju, what is the Roche's theorem?
If f and g are the two functions holomorphic over a domain D such that mod f of z is greater than mod gz over the curve gamma, then f plus g and the function f plus g and f have same number of zeros.
The number of zeros in that domain. Yes, right.
Or
So the given polynomial this, we are defining fz as a n z raised to power n and hz as the other remaining terms, right? Now choose R large enough so that this condition is satisfied. So from using this condition, you can see that mod of hz will be less than this r minus 1. Mod of fz is mod n r raised to power n. So mod of hz is always less than mod of fz. Using this condition, you can observe that this mod of hz is always less than mod of fz. So from there, we can say that f and p both have same roots inside R. We can choose this R large enough. So that which will imply that using the Roche's theorem, you can say that P has n roots. Now this F has n roots. So P will have n. P has n roots. In C, because R is large enough tending to infinity, therefore I am writing here C, that P has n roots in C. Is it okay?
Yes,
Is it
ma'am.
fine? Okay. Now the next question is, yeah. Next question is, show that for any R positive, there exists an integer such that this polynomial has no zeros in the ball for all n greater than equal to n r. We have to show this. Yes. How can you show this? Hello. I'm yes, someone was speaking. Hello. We are defining this function fz as p n z upon e raised to power z and gz function to be equal to 1. We can do that, right? Now, whose growth is faster, polynomial or exponential? Exponential. So from this result, we can choose n large enough so that mod of fz minus 1 can be less than 1 for some radius, ball of radius r. Now you can apply Roche's theorem. You can take this to be hz and this to be gz. Apply Roche's theorem. To get f and g will have same roots. And you can see that g has no roots in this ball. So f root will depend on p and z only. So p and z will have no roots in this ball after for this large n, right? Is it okay?
No, ma'am. Please repeat.
We are defining this function fz, which is p and z upon e raised to power z. Now from we know that the exponential growth is faster than polynomial growth. From that result, we can choose any large n so that mod of fz minus 1 can be taken to be less than 1. हम polynomial की power डिग्री बढ़ा के ये दिस एफ जेड को 1 पे टेंड करवा सकते हैं, और एप्सिलॉन को एक एज एप्सिलॉन को 1 ले रहे हैं लिमिट डेफिनेशन से. Okay, then we are applying Roche's theorem. Roche's theorem says that this g, if mod of hz is less than gz, and then f equal to h plus g, then f and g will have the same roots. So from here we can see that f and g will have same roots, but g is a constant function 1. It does not have any root, which will imply that fz will not have any root. And the roots of fz primarily depends upon p and z only, because niche to ez hai, it does not have any root. So which will imply that p and z will not have any root in this ball.
Okay, ma'am.
Okay. Next question. Next question is, yes, this is the direct application of Roche's theorem. So this given function fz is given minus it. You have to calculate the number of zeros inside the ball B01. So how will you choose G and H? What will be the G function? This is very simple. You can choose G to be e raised to power z and H to be minus z. And you can see that F is G plus H. And mod of Fz will be 1, which is less than 3, which is mod of Gz. Right? So F and G will have same roots inside this ball. Right? So G does not have any root. So therefore F will not have any root inside the ball of radius 1. Is it okay?
Yes, ma'am.
This will imply F does not have any root. Now you can see the C part. For the C part, you have to calculate it twice. Like this was the first A part. You should look at this part. This function given is z raised to power 4 minus fz plus 1. You have to calculate the roots in ball, a ball of 0,2 radius minus ball of 0,1 radius. So first of all, you will calculate the all the roots inside this ball of radius 2, and then you can minus all the roots inside this ball of radius 1. You will get all the roots which are here. Right? So first of all, calculate the roots inside the ball of radius 2. For that, what will be the G function? Yes, Sanju.
Then gz equals to z raised to power 4 plus 1 and hz equals to minus 5 z.
You can also take it like this, because for this you can directly see that it will have 4 roots.
Yes, ma'am.
Yes. So the mod of this will be 16 and this will be some 11. So G will be mod of GZ will be greater than HZ, right? Right. So from here you will get that there will be the 4 roots of F inside ball of radius 2. Yes. Now for the second part you have to uh, calculate the roots inside the ball of radius 1. For that, what will be the G function? Yes, minus 5z. Its modulus will be 5 and its modulus will be 2 and this will be always less than this. So here will be, here has only one root. So total roots inside this will be 4 minus 3, 1. Yes or no? Is it fine?
Yes, ma'am.
And 4 minus 1, 3.
Oh, sorry. Yeah. 4 minus 1, 3. Total roots are 3. Next, question number 2. D is the closed curve. Function is holomorphic inside this curve. And gamma is the simple Jordan curve. Such that no zeros are on the boundary of a gamma. And you have to prove that by iota gamma z raised to power k f dash z upon fz is equals to solution gamma raised to power k. Where this sum is over all zeros off. So what is the statement of argument principle? We will use argument principle in this question. So what is the statement of argument principle? Yes, Bhavna.
Ma'am, if D is a closed curve domain and we have a smooth Jordan curve, and if function is a monomorphic function such that it has no zeros or poles, then integration of 1 over the curve gamma f dash upon f is equal to 2 pi I into z minus p, where z is the number of zeros of f and p is the number of poles of f inside gamma counted with multiplicity.
Yes. And there is one extension of this theorem also. That is 1 by 2 pi I. This gz is a analytic function. You can find the proof of this theorem in I think Conway. This is equals to g of zi minus g of pi, where zi's are the zeros of fz and pj's are the poles. This is the extension of argument principle. We will use this theorem to in the question number 2. Here gz is the given polynomial that z raised to power k. right? Because the function is holomorphic, there are no poles. There are only zeros of f. The function is holomorphic, there are no poles, only zeros, and this function you can take it as gz. Then applying this theorem, you will get that summation of zi is power k, I is 1 to n, or you can say alpha k, where alphas are the zeros of the function f. Is it okay? This is the
Yes.
extension of, this is the, we are directly using the extension of argument principle. Proof of this theorem, you can find it in Conway. Is it fine? Now, first question is left as an exercise for you because time is already up. If you will not be able to do it, you can just mail me. Is it fine? All the cheat sheets are now complete. Hello. All the best for your exams. Your exam is on
10th April, ma'am.
10th.
Yes, ma'am.
Okay. All the best for your major exam. And I think your copies of quiz is also checked. So I will give you the PMT. So, thank you.
Thank you.
Okay. Thank you, students.
Thank you, ma'am.
Okay.